Multiplexer is a device that can select one input from multiple input lines and forward it to only one output line. And for selecting one input line from multiple input lines, we need selection input lines. For 2 to the power n number of input lines, we need n number of selection input lines, and number of output lines will always be 1 in case of multiplexer. The short form of multiplexer is mux. So this is the block diagram of a multiplexer where we have 2 to the power n number of input lines, n number of selection input lines, and only one output line. For example, if we have 4 input lines, then we have 2 to the power 2 number of input lines. So we need 2 selection input lines for selecting one input from 2 to the power 2 number of input lines. And if we have 3 input lines, then also we need 2 selection input lines because we need 3 patterns, and for 3 patterns we need at least 2 bits because with 2 bits we can make 4 patterns. And if we take only one selection input, then we will have only 2 patterns, but we need 3 patterns. That's why we need 2 selection input lines in case of 3 input lines. That's why I have used the term max here. 2:1 mux means we have 2 input lines and 1 output line. So we have 2 to the power n number of input lines where n equals to 1. So we have 1 selection input line for selecting one input from multiple inputs, and this is the truth table for 2:1 mux. We say that when our S0 is 0, the output will be I0, and when our S0 is 1, our output will be I1. And this is the Boolean expression y equals to S0 prime I0 plus S0 I1. So let's see how did we write the Boolean expression for 2:1 mux. So when S0 is 0, our expression becomes like this: 1 into I0 plus 0 into I1. That means we only have I0, so output is I0 when S0 is 0. Similarly, when S0 is 1, this expression becomes like this: 0 into I0 plus 1 into I1 equals to I1. So when S0 is 1, we will get the output as I1. And this is the block diagram where we have 2 input lines, 1 selection input line and 1 output. Our expression is y equals to S0 prime I0 plus S0 I1. So we will need one inverter for this prime, 2 AND gates and 1 OR gate. So this is the logic diagram using this Boolean expression. Now let's see if our logic diagram is working as a 2:1 mux or not. So for the first pattern we are giving S0 as 0, so our S0 is 0, and in that case S0 prime will be 1. So for the first AND gate our one input is 1. For the second AND gate our one input is 0. So for the second AND gate we will always get the output as 0 for the first pattern. That means one of the inputs for this OR gate is always 0 for the first pattern. And for the first AND gate we can see the output is depending on I0. If I0 is 0, then we will get the output as 0, and we will get 0 here because all the inputs of this OR gate become 0 in that case. So we will get the output as 0, which is actually I0. And when our I0 is 1, then we will get the output of first AND gate as 1, and in that case one of the inputs for this OR gate becomes 1, so we will get the output as 1, which is I0. So when we give S0 as 0, we always get the output as I naught. Similarly, for the second pattern, we can see our S naught is 1, so our S naught prime is 0. So for the first AND gate, we will get one input as 0, so our output will always be 0. So one of the inputs for this OR gate will always be 0. And for the second AND gate, we have one input as 1, so the output of this AND gate will depend on I1. If I1 is 0, our output will be 0, and the output of this OR gate will be 0, which is actually I1. And if I1 is 1, then our output of this AND gate will be 1, and the output of the OR gate will be 1, which is actually I1. So for the second pattern, we always get the output as I1. Similarly, for 4:1 mux, we have 2 to the power 2 input lines. That means we will need 2 selection input lines for selecting one input from multiple inputs. So this is our block diagram where we have 4 input lines, 2 selection input lines, and 1 output. And we say when our S0 and S1 both are zeros, then we will get the output as I0. For 0 1, we will get I1. For 1 0, we will get I2, and for 1 1, we will get I3. We can write the Boolean expression like this, and we can check if it is correct or not. So when we are giving S0 and S1 as zeros, then this expression will become y equals to 1 into I0 plus 0 into I1 plus 0 into I2 plus 0 into I3. So I0. If we put S0 as 1 and S1 as 0, then we will get the expression like this: 0 into I0 plus 0 into I1 plus 1 into I2 plus 0 into I3 equals to I2. In this case, our S0 is 1, so here S0 is 1. S1 is 0, so our S1 prime is 1. So this product will result in 1, and the other products will result in zeros. You can check if you want. So we can get only I2 when our S0 is 1 and S1 is 0. And using the Boolean expression, you can easily draw the logic diagram for 4:1 mux. Now let's check the logic diagram of 4:1 mux. Let's check this pattern. Here our S0 is 0, so our S0 prime is 1. Our S1 is 1, so our S1 prime is 0. So for the first AND gate, we get two inputs as 1 and 0, so our output will always be 0. For the second AND gate, we get the inputs as 1 1, so the output will depend on I1. For the third AND gate, we get the inputs as 0 0, so our output will always be 0. For the last AND gate, we get the inputs as 0 1, so our output will always be 0. So these are the 4 inputs of this OR gate, and we can see all the inputs of this OR gate is 0 except the second one, which is I1. So when I1 is 0, then the output of this OR gate will be 0, and when I1 is 1, the output of this OR gate will be 1. So the output is actually I1 for the second pattern. Let's look at another pattern. Let's look at the last pattern. In this case, our S0 is 1, so our S0 prime is 0. Our S1 is 1, so our S1 prime is 0. So for the first AND gate, we get the inputs as 0 0, so our output will always be 0. For the second AND gate, we have the inputs as 0 1, so our output will always be 0. For the third AND gate, we have the inputs as 1 0, so our output will always be 0. For the fourth AND gate, we have the inputs as 1 1, so our output will depend on I3. The output of this OR gate will always be I3 for the fourth pattern. So when our I3 is 0, we will get Y as 0. If our I3 is 1, then we will get Y as 1. So we are getting I3 in the output for the fourth pattern. Similarly, for 8:1 mux, we have 2 to the power 3 input lines. So we need 3 selection input lines, and the number of output lines of a mux is always 1. So this is the truth table of 8:1 mux, and this is the block diagram. Similarly, this is the block diagram of a 16:1 mux. Now let's construct a 4:1 mux using 3 2:1 muxes. This is the logic diagram, and this is the truth table of 4:1 mux. For the first pattern, our S0 is 0, our S1 is also 0. So from the first 2:1 mux, we will get the first input as output, which is I0. From the second 2:1 mux, we will get the first input as output, which is I2, and I0 and I2 are the inputs of third 2:1 mux. As S0 equals to 0, so we will get the first input as output, which is I0. So for the first pattern, we are getting I0 as output. Let's see another pattern. For fourth pattern, our S0 is 1, our S1 is also 1. So for the first 2:1 mux, we will get the second input as output, which is I1. For the second 2:1 mux, we will get the second input as output, which is I3, and I1 and I3 are the two inputs of third 2:1 mux. As S0 is 1, so we will get the second input as output, which is I3. So for the last pattern, we are getting output as I3. Similarly, we can construct 8:1 mux using 2 4:1 muxes and 1 2:1 mux. Let's see two patterns and be clear. If we look at this pattern, our S0 is 0, our S1 is 1, and S2 is 0. So for the first 4:1 mux, we will get the third input as output. For the second 4:1 mux, we will get the third input as output. And these are the inputs of 2:1 mux, and as S0 equals to 0, we will get the first input as output. So we are getting I2 for this pattern. For this pattern, our S0 is 1, our S1 and S2 are 0 1. So for the first 4:1 mux, we will get the second input as output. For the second 4:1 mux, we will get the second input as output, and these are the inputs of the 2:1 mux. And as S0 equals to 1, so we will get the second input as output. So for this pattern, we are getting the output as I5. We can implement any function of 3 inputs using 8:1 mux. For example, here we have a function f of abc equals to summation of 1 2 4 5. So this is in sub form. So we can say we need the outputs to be ones in these positions. If we can give the inputs of the function as the selection inputs of the 8:1 mux and put the outputs of the function as the inputs of the 8:1 mux, then our function will be implemented. Let's see how. For 8:1 mux, if our pattern is 0 1 0, our third input should be selected and we should see the third input as our output. So here our third input is 1 and we will see 1 here. So for the third pattern, we are getting 1. Similarly, if we choose the pattern 110, we should get the 7th input in the output, which is 0. And in the truth table we can see for 110 we should get 0. So in this way we can implement a 3 input function using 8:1 mux. We can implement any 3 input function using 4:1 mux also, and in that case we will require less number of gates because we know we will need less number of gates in case of 4:1 mux than 8:1 mux. In 4:1 mux we have 2 selection inputs, but here we have 3 inputs, so we will use 2 of the 3 inputs as our selection inputs and use the other one as the main inputs of the 4:1 mux. And for using that input as the inputs of 4:1 mux, we need to draw an input selection table for that input. For example, here I have used B and C as my selection inputs and A as the inputs of 4:1 mux. So I need to draw an input selection table for A. For 4:1 mux, we have 4 inputs: I0, I1, I2 and I3. Now we need to find in which positions A is 0. From the truth table we can see A is 0 in the positions 0 to 3. So we can write 0, 1, 2, 3 in this row. Then we need to find in which positions A is 1. From the truth table we can see A is 1 from the positions 4 to 7. So we can write like this 4, 5, 6, 7. Then we need to mark in which positions our output is 1. So I have marked here. After that we need to apply OR operations column wise. For the first column we can see we don't have any 1 in this position, so for A prime we will write 0, and we have 1 in this position, so we will write A, and after applying OR operation the result will be A. So this will be our first input. In the second column we can see in both positions our output is 1, so we will write A prime plus A and the result is 1, so our second input is 1. For the third column we can see in this position our output is 1, but in this position our output is not 1, so we will take A prime plus 0, which is equal to A prime. So our third input is A prime. In the fourth column we can see we don't have any 1 in any of the positions, so we can write 0 plus 0, which is 0, so our fourth input will be 0. And that's how we implemented the function using 4:1 mux. Let's check if our design is correct or not. For 4:1 mux, if we take the selection inputs as 0, 0, then we will get the first input as our output. So here our first input is A, so we should get A in the output. From the truth table we can see when our BC are 0, 0, then our output is equal to A. When BC are 0, 1, we will get the second input as output. From the truth table we can see when BC are 0, 1, we always get the output as 1. If BC are 1, 0, then we will get the output equals to A prime. So when BC are 1, 0, we get the output as A prime, because here A is 0 but our output is 1. Here our A is 1 but our output is 0. When we take BC as 1, 1, then we will get the fourth input as output. In this case our fourth input is 0, so we will get output as 0. So for 1, 1, we always get the output as 0. Now I have used A and B as my selection inputs, and I have used C as the inputs of 4:1 mux. So I need to draw an input selection table for C. I need to find in which positions C is 0 and in which positions C is 1. So in these positions C is 0 and in these positions C is 1. You can check from the truth table. In the position 0, 2, 4, 6 C is 0 and in the positions 1, 3, 5, 7 C is 1. So we can put like this. After that we need to mark in which positions output is 1. So in these positions our output is 1, 1, 2, 4, 5. Now we need to apply OR operations column wise. From the first column we can see we don't have any 1 in this position, but we have 1 in this position, so we can write 0 plus C equals to C. For the second column we have 1 in this position, but we don't have 1 in this position, so we will write C prime plus 0 equals to C prime. In the third column we have 1 in both positions, so we will write C prime plus C equals to 1. And in the fourth column we don't have any 1 in any of the positions, so we will take 0 plus 0 equals to 0. So these are our 4 inputs of the 4:1 mux using C. Previously we have seen we can implement 3 input function using 4:1 mux, so we can implement 4 input function using 8:1 mux. For example, this is our function which is of 4 input. Here I am using B, C and D as my selection inputs and A as my main input. So I need to draw an input selection table for A. I need to find in which positions our A is 0 and in which positions A is 1. Then we need to mark in which positions output is 1. After that we need to apply OR operations column wise, and in this way we will find the 8 inputs of the 8:1 mux. So this is the truth table for this function and this is the block diagram. In full adder we have 3 inputs, so we can implement full adder using 4:1 mux. In full adder we have 2 outputs, sum and carry, so we will need 2 4:1 muxes. So here I have implemented sum and carry using 4:1 mux. This is the logic diagram and this is the truth table of full adder. We can implement full adder using 8:1 mux. Let's see how. In full adder we have 3 inputs, but now we will use an extra input which is SE. When SE is 0 we want our output as carry, and when SE is 1 we want our output as sum. We will use the inputs A, B and C as the selection inputs of 8:1 mux, and we will use SE as the inputs of 8:1 mux. So we need to draw an input selection table for AC. We need to find in which positions AC is 0. From the positions 0 to 7 AC is 0, and from the positions 8 to 15 AC is 1, and we have output 1 in these positions. So after applying OR operations column wise we can find the 8 inputs of the 8:1 mux. This is the logic diagram of full adder using 1 8:1 mux, and this is the truth table.